All right. Is everybody signed in? All right, let's get started. First of all, any questions on any of the homework problems yet? Well, got one that we're going to look at. I want to back up and I want to do this. Somebody asked about this one last time. This is, I think, number 16. I tried to show y'all how to set it up to do it. I want to work it through a little more thoroughly and show y'all how to actually go through the whole problem. We're going to begin by describing the setup. The charged spheres are separated, swinging their 78 centimeter lines through 20 degrees. They're 21 grams each, and they have a total charge between the two of them of Q, half the charge on each sphere. Start by looking at the forces that are actually at work here. This is the force due to gravity. And there's this force due to the Coulomb repulsion. So we got gravity and Coulomb. The net force on this is then the vector sum of these two. All right? Of course, why is the ball not moving? If there's a net force pushing it in this direction, it's not moving because the wire is maintaining an opposing force and tension in the opposite direction. That's why it's static. It's not moving. We can calculate the force due to gravity as 21 grams times the acceleration due to gravity, 9.8 meters per second squared. We cannot write down yet a value for the Coulomb force. But we can find this one. And if we actually do the arithmetic, always my favorite part, right? 21 times 9.8. Whoop. I should put that in kilograms, shouldn't I? See, this is why I hate the arithmetic. There's always these little things that will sneak in and get you. How many kilograms is 21 grams? 0.021 kilograms times 9.8 and that gives us 0.2058 newtons, kilograms, meters per second squared. What do we know about the relationship of this force vector to the sum of the two vectors? These angles are similar, so we know this is 20 degrees. And we can immediately write F total, which is the sum of the two vectors, times, and I wrote an equal sign, times the cosine of 20 degrees is equal to this force vector, 0.2058 newtons. So if we divide that by cosine of 20, we get a total force vector magnitude of 0.219 and some zeros and a 7 newtons. That's how we determine this magnitude. How then would we determine this magnitude? Well, we could do a bunch of conversions and do subtracting this vector from that vector. We can convert them both into right rectangular coordinates and subtract them and then convert the result back into polar coordinates. Or we could just multiply the magnitude of F total times the sine of 20 degrees, which will give us the magnitude of this force. .075 newtons.
On the FT on the cosine problem, you're just taking the 0.2058 newtons over the cosine 20, right?
Right. I'm dividing both sides by cosine 20. You did? Well, then was one of us in degrees and radians? Oh, then you would have gotten a whole different answer. It's, yeah, we're working with 20 degrees. I'm sorry? No, I'm dividing both sides by cosine 20 to eliminate cosine 20. From here, leaving just the magnitude of the force vector on this side and giving me the value here. Now, let me show you one more trick. In case this isn't, well, before I do this, let me ask you, is everyone clear on how this is done now, what we just did to solve this problem? We have this vector, this magnitude, that's an unknown magnitude, times the cosine of this angle, 20 degrees, not radians, gives us would give us the magnitude of this vector, which we know is this many newtons. So we have some unknown times the cosine of 20 degrees is equal to this many newtons. We divide both sides by cosine 20, and that gives us this magnitude. Now, we divided this value here by cosine 20, and that gave us this. We then multiplied it by sine 20 to get this. Does anyone see what we could have done? We could have just multiplied the times the tangent of 20, and we should have gotten the same answer. Now, should have. Let's verify and see if we actually do. What was the magnitude of the force vector, the gravity? 0.2058 times 20 tangent, 0.0749 or 0.075. I pointed this out because it occurred to me that you got to this point, some of you might have started doing the bigger hammer approach of, okay, well, I've got to convert these into rectangular coordinates so I can add them, and I've got to convert that back and then subtract the difference and go through all of that. Always look for the easiest way to get to the answer. Any questions? Everybody good so far? Okay. What I want to do today is finish up chapter 16, the material that we're going to cover. How many of you have looked at the syllabus? Let me rephrase the question. How many of you have seen what's coming up Monday? First exam. How many people here believe you're ready to pass that exam? Anybody? One confident soul in the room, and it ain't me. I really want y'all to be ready to pass this exam. So what I'm going to do is I'm going to try and finish off this chapter material today. And then I want y'all to come in on Friday ready to ask questions. You're going to be 2 days away from turning in a homework assignment. Hopefully by then you will have started working on it. You'll have questions, and understand, I desperately want to explain all of this to you in a way that makes sense. My conflict is if I start explaining little tiny minutia, then I'm going to lose you because you're going to be sitting there going, oh man, how stupid does he think we are that we don't understand it? We learned that 2 years ago. Okay? The problem is if I go the other direction, I start zipping over things that might be intuitively obvious to me that you've never seen before. I don't know how many of you have seen how you add and subtract exponents to do multiplication and division on scientific notation. Those of you who have seen it, if I start explaining it in detail, you're going to get bored in a heartbeat. Those of you who have never seen it, because I know this from experience, it happened to me when I was in undergraduate school. The professor started doing all this stuff and coming up with all these wild answers just out of his head, and it's like, how's he doing that? It took me two lectures before I finally put my hand up and said, stop. How do you do that in your head? Show me your trick. That was the first time anyone showed me how to do that. The point I'm trying to make is I need feedback from y'all. There's pretty much all of this stuff I can explain to you in ways that will make it make sense. But I need to know what I need to explain. And to know that, I need feedback from y'all. So, Friday, come in ready to ask questions. We will work on problems from your homework that are giving you difficulty. Things that you haven't quite figured out, you don't quite understand. We'll work through them step by step. Yes, that means you're going to be getting some free homework points. Whoopee! 7 lousy points. I will give you those points if it'll help you to understand the material. The exam on Monday is the bulk of your grade. That's where the bulk of your grade. The homework is intended to be free, cheap, easy points. I encourage you to work together. On the exam, it's cheating. In homework, it's collaboration. Okay? On the homework, I will help you if you ask for the help. That's why I always, you may have noticed, I start every class. Any questions from what we've done so far? Any questions from the homework? Okay? I can't spend the whole class doing that because we wouldn't learn anything new, but I am scheduling a day for review before the exam for that very purpose, so come prepared. Now, we were talking about E fields, electric fields. Yeah, that's no, I'll deal with that in the lab. There was one question on that lab y'all did yesterday. I'm in the right class. Yeah, y'all, it was your class yesterday, Physics 2. There was one question on that lab that everybody got wrong. So I'm going to give everybody the point for it, but I want to make sure we cover where y'all went wrong. I think one person got it right. Okay? And no, don't ask because I don't know who. I don't look at the names on the papers when I'm grading them. But it was the one about it was like the last one about when you bring the acetate strip. You know, what is the charge on the on the electroscope, and and I think pretty much everybody said it was negative. You know what? I'm not going to try and guess. We'll go over it very quickly next week in the lab. But I do want to make sure y'all all understand that one. Electric field. E. Where's my marker? Found one that was writing for a little while. I don't want to lose it. The force divided by Q, the charge. Which means that we can write the equation for force on a charged particle as Q times the electric field. Make sure that, got this. Again, quick note, I want to make sure I told everybody for the test, all you'll need is paper, pen, calculator, and you can each have a 4x5 or a standard index card. Write what you want, what you need on both sides. Okay, cheat sheet, whatever you call it. Just, you can't write the questions in advance. And if any of you have already gotten the questions that are going to be on the exam Monday, get with me after class. We're going to Vegas because I haven't made them up yet. Going back to this top one, we can, using Coulomb's law, we can write this force as the constant K times Q times the charge that's generating the E field divided by R squared. And then divide that by Q. And we see what happens. The Q's of the test particle that's being tested cancel out. Which leaves E as being equal to KQ over R squared. And how can we rewrite K? One over 4 pi epsilon sub naught. Now this should just be review so far. This is what we covered last time. We also talked about electric field lines and that they emanate from, and this is by arbitrary definition, but we consider that they emanate from positive charged particles and they go to negative charged particles. And the math would all work out the same if we, or the physics would all work out the same if we reverse those two. This is the accepted standard definition, so this is the way we will continue to treat it. And did everybody look at some of the examples of the E-field lines in the book? On, what's this, page 458, it shows you these examples of dipole, where you have unlike charges. And then it shows you the example where both charges are the same. This middle one is where you have two positive charges and a single negative charge. Then it shows you this with the two parallel plates. And that's where we want to pick up today. We're going to talk about electric fields and conductors. Let me clear me out some writing space. Have any of you read ahead in the chapter? All right. Well, let's see what we can. First thing you need to know is that in a static situation, now this changes when you have an electric current flowing in a conductor, but in a static situation, the E field inside any conductor is always zero. No E field. Why does that have to be the case? Think about the structure of a conductor. What makes a conductor a conductor? There's no current because there's no E field. Yeah, but exactly. A conductor, by definition, has all these free electrons that can move around easily from atom to atom. If there was an E field inside the conductor, as he pointed out, it would exert force on those electrons and cause them to move. And since they don't move, since everything is static, the E field inside the conductor must be zero. So now what happens when you subject a conductor to an E field? Well, the charges, that the free electrons, the free charges that are in the conductor free to move, will immediately move towards the surface, and they will then distribute themselves on the surface of that conductor in such a way as to minimize the force they're exerting until they reach equilibrium. They will just uniformly cover the entire surface of the conductor. But inside the conductor, they will go back to zero. They will produce whatever E field on the outside of the conductor they must in order to reach equilibrium. But inside the conductor, the E field will go back to zero. How many of you do electronics? All of you. How many of you have done any printed circuit design? Printed circuit design. High-speed digital electronics. Yeah, but have you ever built one? Have you ever actually built a circuit board for a microcontroller? No. When you start working on high-speed digital circuits, when you're designing the circuit board, you are going to find out real quick that this stuff is important. And you start having signals reflected back and forth on these conductors, and what you learn is that in the time, you learn that electrons move, they don't move as fast as you think. It's the potential, it's the E field that propagates in the conductor. And it propagates at the speed of light. But that means that it takes about a nanosecond for an E field to propagate, or a potential to propagate roughly a foot. I think it's like 11 inches or something in a conductor. Okay. Well, if your circuit is switching, if the time it takes your voltage on your output from your circuit to drop from VCC to ground is less than a nanosecond, then that means that for a period of time, some finite period of time, you're going to have a different voltage at both ends of that conductor. That means that signal is going to actually start propagating like a wave. That means it's going to start reflecting back and forth and give you all manner of problems. That's why among circuit board designers, the ones who work on high-speed digital electronics, the rest of them just write it off as black magic voodoo, and they don't worry about it. They ignore it. It's like, I'll stick to transistors and LEDs. And let the wizards do the high-speed digital stuff. Anyway, get back to the lesson. Electric fields and conductors. Inside the conductor, it's going to be zero. Now let's look at an example here where we start with a spherically symmetrical conductive shell. Let's put a positive charge inside it. Those E field lines are going to extend right up to that shell. And what's going to happen? They're going to attract all those free electrons. And I'm not going to try to draw them all the way around, but they're going to attract all those free electrons to that inner surface, so that all of these E field lines will have something to terminate on. But now what happens when all of these electrons congregate on the inside surface of this metal, this conducting sphere? They are now going to repel the positive charges uniformly on the outer surface. And in fact, I'm going to draw them as continuations. All of these E field lines will continue right on from the outer surface of the sphere. This is called induction. This positive charge is attracting the negative charges to the inside surface, which then forces the positive charges to repel and to congregate on the outer surface. So, when you get out here and you look at the E field right here, you see the same E field that you would from this point charge. Now, here's an example they give you in the book of two parallel plates. And they make the point of shielding. You start with a parallel plate here and put a hollow conductive box in the middle. Now, if this plate is charged up positive, this plate, when this positively charged plate here has all the positive charge, because it's a conductor, so all the charge is distributed on the surface, and it produces an E field. Okay, now at the edge, you're going to see some fringing effects. Okay. But you'll notice the lines get much further apart in that fringe area. We're generally going to ignore the fringing areas of these field effects. We're going to concentrate on the inner part. The positive charges on this plate induce the negative charges on this plate and set up a field, an E field between them. Again, I said the positive charges induce the E field, the negative charges on the opposite plate. You could just as easily consider it the other way around. The negative charges build up on this plate and induce the positive charges on this plate. In fact, that's generally the way I think of it, because I think of electrons as the actual particles that move around. But either way, it works the same, and you end up with this perfectly uniform field. Now, consider what happens to this box in the middle. It's a thin metal conductive box. What does the E field inside this box look like? And the answer is nothing. There is no field inside that box. The field here induces negative electrons here. Those, in turn, produce positive charges over here. What about on the ends of this box? No, well, yeah, if we were to get down to the microscopic level and look at it, that we would find some fringing effects here. We're going to ignore those. Remember, the force of the E field that the E field exerts on the conductor is, maybe we haven't covered this yet. So if we haven't, I'm telling you now. It's a vector equation. That means because the vector field here is parallel to that end plate, it doesn't have any influence. Ignoring fringing effects, there's basically no charge down here, no E field emanating from the end here, because it's parallel to the E field. And we're going to cover that in a little more detail in a minute when we get to Gauss's law. But right here, the point I want to make is that if this block of metal were a solid block of metal, then we know that there's no E field inside it because it's a conductor. What I'm telling you now is that even if it's a hollow metal box, because there's no interaction on the end here, there's not going to be any E field inside it either. Because all of the charge is going to redistribute on the outside surface to produce an uninterrupted, to not interrupt the E field from going, neglecting fringing effects. This is why shielding works. This is why if you want to protect a circuit from electromagnetic, from RF interference or something, put it in a little thin metal box, shield it. That's how shielding works, especially if you ground that shield. Now, what I want to explain to you now is why the E field on any conductor, and this is again, comes back to this end effect here. Why is it the case that the E field on any conductor must always be normal to the surface of that conductor? And everybody understands what I mean when I say normal. orthogonal, perpendicular. Okay? Let's say we have a curved surface. It's randomly curved. It's not a well-defined surface. We've got an E field. Let's assume we had an E field coming off of the surface of this conductor at an angle theta. Let's assume that that's possible and that it could happen. What would be the consequence? Can everybody over there see? Okay. Well, let's decompose this vector. Take a normal line to the surface and a tangent line to the surface, and we would find that this angled vector E field would actually consist of two components, a normal or orthogonal component and a tangential component. But what would happen if it had a tangential component? It would produce tangential motion of the electrons, and they would start to move. Or tangential motion of the charge. Whether it's electrons or positive charges, it doesn't matter. If there's a tangential component, if the E field emanates from a conductive surface at an angle other than normal, other than orthogonal, then it's going to have a tangential component to that vector that's going to produce motion of acceleration of the charges in the conductor, and they're going to move around and redistribute themselves until they stop moving. Well, if they have stopped moving, then we know that this component has to be equal to 0, which means this must be completely in the perpendicular, completely orthogonal. That is why you cannot have an E field emanating from a conductor at an angle. They will always come off of every conductive surface, no matter how irregular it may be, normal to that conductive surface. And I'm going to skip right over biology and photocopiers. And we're going to finish up this chapter on Gauss's law. And I think everybody here has had calculus, right? Okay. We're still going to do this non-calculus, but how many of you are already familiar with Gauss's law? Or have any of you seen Gauss's law yet? No? Okay. Well, Gauss's law treats the E field as a flux. What do I want to erase? I'm going to erase this. Okay. We talk about just an electric field passing through some randomly chosen area. if we take the, oh boy, this is, you might want to look in the book at these pictures. They're on page 463 because my drawing is not very good here. That surface, the line perpendicular to that unit area of surface subtends an angle theta to the E field. Then we can talk about the flux of this E field that passes through this unit area as being E times the unit area, like a cross section, times the cosine of the angle, theta. Now, why the cosine of the angle theta? Remember, this we're defining this as the flux density phi. Okay, of the electric field. Think of the flux or flux density as the density per unit area of those electric field lines. So, how many are passing through this unit of area depends on the angle between them. Just imagine that angle of area, imagine that unit of a surface area rotating through theta until theta equals 90 degrees. Well, now it's parallel to the E field, to the electric field. And once it's parallel, that plane is parallel, then none of the E field is passing through it. In order to get the maximum flux density passing through the area, you would have to put it orthogonal. I'm not going to try to draw it because it's already hard to read, but you'd have to put that unit area orthogonal or perpendicular to the E field. So, Gauss's law gives us this equation as an expression of how much E field, how much flux is passing through a unit area. I hope I haven't just completely buggered that explanation. Everybody understand what I'm talking about here? We're talking about the amount of this flux, this E field, how much of it is passing through this little area of space. And it depends on how that area is oriented to the field. When they're perpendicular, you get maximum flux through the unit area. When they're parallel, you get zero. And anywhere in between, it's proportional to the cosine of the angle. Now, I want to follow this through the book as best I can. I guess I'm just going to cut straight to the chase. Because Gauss's law, this is what it's based on. This is not Gauss's law. This is just an explanation of how much E field is passing through any unit area. This is Gauss's law here. The sum of the E field passing through a unit of area, or a small piece of area, let me just write it and then I'll try to explain it. Suppose you took just an arbitrarily shaped three-dimensional surface, and you put some charge inside that surface. Then if you took it's not dashed. Draw all the flux lines coming out. If you then integrated, didn't mean to say it, actually this equation does translate into an integral equation when you're doing this from a calculus perspective. We're still going to stick with the discrete incremental summation notation. You go through and you divide this whole surface into little tiny areas. And you multiply the E field emanating perpendicular to that area, to that little unit area, times that little delta area, that little bitty tiny piece of area, until you added up the whole surface. Then it would equal the charge enclosed divided by epsilon naught. And I think this is a better way to do it. We're going to now. This is true for any arbitrary random surface, no matter how squiggly or oddly shaped it may be. As long as you multiply every area times the flux coming, times the E field coming out of it, you're going to end up with the total charge enclosed in it divided by epsilon sub naught. Now, let's look at a more specific example, one which, as will usually be the case, when you're working with Gauss's law, you're going to choose your surface that you add up, that you sum over, or if you're doing it in calculus, that you integrate over. Because it would be a real problem to try and add up all the little increments of area around this oddly shaped surface. But what if we go back to our conductive sphere? We've got a conductive sphere here. It's a thin metal sphere that's hollow on the inside. Oh, now let's say we have a charge Q in it. We have E fields, lines emanating from it. And everywhere, because of the way this E field induces, what do we know? We know that everywhere on the surface of that area, of that conductive sphere, the E field is normal to the surface, right? So the cosine of the angle is going to be 1. I went through this problem, and we know that E is everywhere perpendicular. Yeah. So the sum, because the E everywhere over this field, the E field everywhere on the surface is perpendicular. We know that the sum of all the little delta, all the little individual pieces of the total E field are going to be the total E field. And that leaves us with just the sum of all the little delta areas. And that'll be equal to Q over epsilon sub naught. Well, what's the sum of all the little tiny areas? And it is the end of the... Real quick, if you sum up all the little discrete pieces of area, you end up with the surface area of the sphere. The surface area of the sphere is... there. This becomes 4 pi r squared. It's Q over epsilon sub naught. Okay? And when you divide both sides by 4 pi r squared, you end up with which you should recognize as what we started with before. And yeah, I see I'm out of time, so Friday, come prepared with questions from the homework, and we will probably, I will pick up again here. I want to cover one more example with you on this Gauss's law.
Last class.
Oh, thank you.